Good evening. This is a continuation of sixth lecture, sixth series. Yesterday we have taken a 1 hour session. After that we have, because of the internet connection, we lost it. So this is a continuation of air pollution and comfort. So we'll try to cover the whole portion as per the GATE syllabus is concerned. Do not leave the class in between. Finish at 5:09. This is right now 4:09. Okay. Yeah. So we were here last time. We were discussing about the air pollution, various pollutants, various impact on human being as well as the planet, environment, and on animals, wild animals, and aquatic life. The sources we were discussing last time, the various sources of air pollution, the contribution from the various sectors, industries, transportation, statics. We were talking. When we were talking about the classification of the air pollutant, we are primarily defined in primary air pollutant as well as the secondary air pollutant. Based on the nature also we have defined organic pollutant and organic pollutant. Based on the state of matter also we have defined particulate matters in liquid forms, solid forms, and gaseous forms. Based on this we have like in the liquid forms we called as mist, gaseous forms we have the various gases, and solids in form of dust, PM 2.5, PM 10, and smoke is also coming in this state of matter form. These are the criteria of the pollutant that we have discussed yesterday. Now we were talking about the concentration part last time. All the gases laws will be applicable here because liquid is different and gas is different. So, like you generally consider 1 ppm or 1 mg per liter will be the same meaning, but here it is not like this. 1 ppm is not equal to 1 mg per liter for the air. So gases law is valid for it. PV is equal to RT. And then if you want to determine the value of concentration carbon monoxide present in a water, suppose in a one question it's given 9 ppm, so 9 mg per liter if you write it. If you this will be the wrong calculation. So for that we have to do some conversions, so that we have yesterday class I have explained this thing. And finally 1 ppm is equal to 1 part of any gas divided by 10 to the 6 part of air. And then finally we have this one. So 1 ppm at the standard temperature and pressure will be equal to m divided by 22.4, the molecular weight of a substance, divided by 22.4 into 10 to the 3 microgram per cubic meter. So concentration generally of the gases we are going to measure in a microgram per cubic meter only. So we have done this numerical last time. Okay. So 9 ppm of carbon monoxide at STP. So there's a 9 ppm means 9 into m divided by 22.4 and 10 to the 3 microgram per cubic meter. So m will be the molecular weight. So that is 12.6, 12 plus 16, and then if you do the calculation, you will getting as 11,250 microgram per cubic meter. So it will be around roughly 11.25 mg per cubic meter. So like this, the same thing you can do the concentration of chlorine, CHCl3. So this will be equivalent to 0.4 microgram per cubic meter is given. In the reverse manner also you can do in that way. So if the concentration is given in in the microgram per cubic meter, then you will get it in ppm also by using this relation. So here it is a reverse. So 1 microgram per cubic meter is equal to constant divided by m into ppb, ppm. That calculation you can do, you will get it finally 0.0 pp. The next question that like 120 microgram per cubic meter of SO2 into ppm and ppb at temperature 10 degrees Celsius and pressure is 1 atmosphere. We have to convert it. So this is the formula that we have just now discussed. 1 microgram per cubic meter is constant divided by m. So like this, you can do the respective conversions. Small questions they may ask in a questions from the GATE point of view. So these things, 2 marks or 1 marks questions. So the same like the convert 40 ppb of nitrogen dioxide into microgram per cubic meter and ppm at temperature 20 degrees Celsius and pressure 1 atmosphere. These are the things that you can do it. So the major air pollutants, like these are particulate matters which play an important role. The total suspended particles, um, the size of suspended particulate matter is 0.01 micrometer to 200 micrometer. It causes the respiratory diseases. So there is the particulate matter called as respiratory suspended particulate matter, or RSPM. So it's like it's not visible, very less size. Micron is very less size. You cannot see from human eyes, but it can easily disperse into the air. It can, while you are breathing it, these particles can particulate matters can easily inhaled, and then it creates a lot of problems for the lungs as well as for the respiratory tract damage. So particulate are of mainly two types. There is a solid particulate like dust, smoke, fumes, flies will be coming in the solid particulate. There's a liquid particulates which will be having mist and spray. There are some aerosols also, solids on liquid particulates of size less than 1 micrometer, which always remain in suspension in the atmosphere. The particulates in atmosphere are measured by high volume samplers. So high volume air samplers are required for measuring this concentration. So while they are going for the measurement of the pollution, there are the various devices that you have to use it for it. There's a total suspended solids, suspended particulate matters. Yeah, suspended particulate matters that you generally measure in microgram per cubic meter. So if you have a high volume air sampler, so initial volume you have to note it down for the filter paper, and then final volume after the accumulation, yeah, after the clogging of the suspended particulate matter on the filter paper, weight difference will be there. So final weight minus initial weight of the filter paper divided by the volume of the air sampler. So you will get the complete like volume of suspended particulate matter in microgram per cubic meter. So like this. Suppose the initial weight of filter paper is 9.787 gram is given, and final weight is after putting a volume sampler for a certain time, and 10.283 gram final. So initial rate of air sampling is given as 1.5 meter cube per minute. Initial rate of air sampling, which is 1.5 cubic meter per minute. Every minute that air sampler is taking a 1.5 cubic meter of air. Average rate of air sampling you can determine through this. There's a 1.5 plus 1.4 divided by 2, 1.45 meter cube per minute. There's the initial rate and final rate is given as 1.4 cubic meter per minute. So the average you can take it. And volume of air sampled in 24 hours, 1.45 into 24 into 60. You will get it in minutes. 1.4 into 24 into 60 total volume of the air sample you can get it. Now TSP you will get it here through this final minus initial multiply with 10 to the 6 divided by 1.45 into 24 into 6 divided by the volume of the air sample. So you will be getting us 237.55 microgram per cubic meter, and that way you are going to calculate the suspended particulate matter volume and your rate of suspension in microgram per cubic meter. Like this you have to estimate it. So we'll go for the carbon dioxide next gas, which is the inert gas. Carbon monoxide react with the hemoglobin in blood to form toxics. So carbon monoxide plus hemoglobin, it forms the hemoglobin, carboxyhemoglobin, which is asphyxiant. We have called as toxic chemical substance the measurement of that particular pollutant is available into the atmosphere. So measurement is important. So one by one we are talking about the measurement. Impact we have already discussed in the last class. Various impacts on the human being, animals, and water animals, and the climate and environmental we have studied. And various types of pollutants also we have discussed. And every pollutant how it is adversely impacting the environment, how it is adversely impacting the human body. That also we have discussed. So I'm not repeating that. Okay. Then oxides of sulfur There are several ways to measure the same way you can uh, like the measure the volume in microgram per cubic meter. So SO2 damage buildings, marble structures, affect plant life, mucous membrane of respiratory tract, respiratory irritations. SOx are measured by West or GATE method. SO2 and SO3 are most dangerous. So suppose the question is given a thermal power plant containing a coal of 5 tons per hour containing 2% of sulfur. Find the sulfur dioxide emissions from the plant in gaseous form. So there's a coal thermal power plant. 5-ton coal is required per hour. It contains 2% sulfur. So sulfur dioxide emissions you have to measure it. So sulfuric, there's a sulfur emissions. You can measure like this. 2% means 2 by 100. Where we have came, yeah. 2% means 2 by 100. Multiply with 5 tons per hour it is given. So 5 tons, 5 into 10 to the power 6 divided by 3600. So you will get it here at 27.78 gram per second sulfur emission total. So S plus O2 will be the SO2 and the molecular weight you can calculate. There's a 32 parts S, 62 parts SO2. So SO2 emissions will be 27.78 multiplied with 2. So you'll be getting a 55.56 gram per second. This is the emissions which will be released from the thermal power plant. So like this, you can measure it. There's a volume sampler where you are going to collect the these gases in microgram per cubic meter. Yeah. Then NOx. NOx measurement is also necessary. NOx sampler and SOx samplers are there. We do have in our laboratory also volume samplers and analyzers also, like NO2 analyzer and SOx analyzer. So NOx damage respiratory component in lungs, plant lives, etc. NOx are estimated by Jacob Ostrander method. The rate of NOx emissions will be equal to 2 gram per kilometer per vehicle. It's a moving vehicle. I have told about the sources of the pollutant, moving sources, fixed sources, right? Point sources, non-point sources. The classification of source of pollutant we have discussed in last class. So based on this is a moving source of pollution. So NOx emissions are coming 2 gram per kilometer per vehicle. So number of vehicles around suppose 50,000 if you consider in a particular city. Distance traveled will be equivalent to 20,000 kilometers. So quantity of NOx produced, you can measure it. 2 into 10 to the power minus 6 into 50,000 into 20,000, you will be getting us 2,000 ton of NOx gas from the city. Okay. So like this, you can estimate it. Now hydrocarbons. These are the unburned fuel actually, while the fossil fuel based emissions, liquid petroleum, gasoline, petrol, diesel, kerosene, and various complex chains of hydrocarbons, and the coal also. So it's a group of compound consisting of carbon and hydrogen atoms, either evaporated in the atmosphere from the petroleum fuel supplies, petrol, diesel, etc., or are emitted out in the automobile exhaust, as they did not burn completely. Just a second. Yeah, we have numbers. Okay. Session, so we'll see in the class. Okay. Did not the fumes of oil refineries. These are the main sources of hydrocarbons, except petrol, diesels, and kerosene and all that. The fumes of oil refineries and incinerator smokes. So most of the cases we are using incinerator in most of the industries like various automobile industries, various thermal power plant, as well as in an incinerator based waste to energy plant, we are using incinerator smoke. So that smoke is also having unburnt fuel. Wash away with these all pollutant hydrocarbons once the rainfall occur in a particular area. These all pollutants hydrocarbons will wash away with the rain and run into the surface water, causes oily film on the water surface. High concentration causes eye and respiratory tract problems, causing body cancer also. And then low concentration, that much of significance is not there. And exposure of high concentration of hydrocarbons causes the lung cancer also. So these are again the adverse impact on a planet as well as on the human being life. Okay, so there is body cancer and lung cancer will be the reason because of the hydrocarbons. So hydrocarbons are measured by the gas chromatography. There's a gas chromatography analyzing mechanism. This is the laboratory analyzing mechanism of various gases. There's a liquid gas chromatography, gas chromatography. There's various type of gas chromatography. It's experimental analysis method. So while you're analyzing the gases, because analyzing the gases is more difficult than liquid, uh, and storing the gases is also very difficult. There are various properties. Every gas has various properties. Some of the gases are highly active in the atmosphere, highly chemically reactive, right? And some of the gases are very ignitable in the nature. So we have to understand the various properties of the gases. So hydrocarbons estimation can be done by the gas chromatography method. There are the two categories. One is the aliphatic group of hydrocarbons, and some second one is the aromatic group of hydrocarbons. If you have studied about the organic chemistry, then you can understand the aliphatic group of hydrocarbons and aromatic group of hydrocarbons. Okay. So aliphatic groups of hydrocarbons like alkanes, methane, alkenes, olefins, and alkynes. Olefins are more dangerous, alkynes, right? So alkenes, olefins are found to be harmful. Non-methane type of aliphatic hydrocarbons under ambient quality standard condition is 160 microgram per cubic meter. I will come for the national ambient air quality standards later on. There are the air quality monitoring index. There is air quality index as well as national ambient air quality index that you have to maintain. These are the standard emission standards. Like the we have a water effluent standards, right? Drinking water effluent standard, industrial water wastewater effluent standard. In the same way, we have a air quality standards also. So the various pollutant is releasing from the various industries. So what should be the standard limit? Someone has to there to control, right, and regulate. Central Pollution Control Board and all that. They have, and then Environmental Protection Agency (EP) has decided the standards. So how much CO2 can be accepted, how much hydrocarbons can be accepted in the particular atmosphere, and how you will decide the green zone, red zone, and yellow zones, and severe zones, and sensitive zones, right, based on the air pollution, or what is the percentage of air pollution that we are getting in a particular area. Suppose the particulate matter, the assessment of particulate matter is getting very high, more than 300 to 400 microgram per cubic meter, means this area is called as very sensitive. So I will be talking later about the zones in all that air quality monitoring standards, right? So hydrocarbons released from the sources and travel into the atmosphere due to the dispersion and dilution. These are dispersion and dilution. These are the both techniques and natural methods for reducing the air pollution and pollutant into the atmosphere. I will be talking later about dispersion and dilution detail. Their concentration reduces into the atmosphere. So dilution and dispersion both depend on the natural weather condition because it's natural purification process. I'll be coming for the dispersion and dilution. Both are the natural processes. Generally, if you see, a dispersion means a spread actually. So once the air pollutant is accumulated somewhere in that area, once it is released from the source, it has to spread in the air, right? Some of the time it depends on the various climatic condition, what is the temperature, what is the wind speed, and what is the pressure, right? So all the factors, climatic factors play a very important role while the dispersion is happening. More dispersion is happening means the pollution is more following matters are first is the temperature, second is the lapse rate. I will be talking about the temperature, lapse rate, and pressure one by one. Then, simple terms, dispersion means spread, dilution means mixing. Depend on the wind directions, temperature, and then pressure conditions into the atmosphere. We have already classified the various spheres: mesosphere, ionosphere, stratosphere, troposphere, all that. There's a temperature range and there's kilometer in height. So with respect to altitude, with respect to height into the atmosphere, these various layers will depend. So temperature is the measure of heat energy. Number one, Lapse rate is the change of temperature with altitude. So there's a change of temperature on y-axis and altitude. No, there's a uh, altitude will be on a y-axis and height, and then temperature will be on x-axis. Then once you plot this graph, once you slope this, I will be going for the graph and all that. Slope it. So change of temperature with altitude will called as the Lapse rate. This is very important while you are deciding the condition of the weather, condition of the pollution label into the atmosphere. So Lapse rate play a very important role for the meteorological point of view. So I will be talking about the one by one all those things. So this is the Lapse rate. In the troposphere, the temperature of the ambient air normally decreases with an increase in the altitude. This is the common theory, right? In the troposphere region, the temperature of the ambient air normally decreases with an increase in the altitude. The rate of change in temperature with altitude is called as Lapse rate, and this rate will differ from place to place. These are the terminologies and technical terms that we are going to use it while you are analyzing and measuring the pollution. Once you analyze, once you measure the quantity of pollution, then you can find out the solution. So the control and measurement control part of the pollution will be different. So I will be talking later, right? So this rate will differ from place to place and from time to time, even at the same place, which can be determined by sending up balloons equipped with a thermometer, and self-recording mechanism is known as the ambient lapse rate, or sometimes we called as the environmental lapse rate. From now onwards, we will be calling as the ELR, yeah, environmental lapse rate. So what is environmental lapse rate? How to determine it? There is a balloon, you have it. You are sending up this balloon equipped with the thermometer. So with respect to height, balloon will go in a vertical height into the atmosphere. Based on this, the temperature range it will be recording. There's a self-recording mechanism there for the temperature and height, and then automatically the graph will be plotted between the temperature range as well as with the height. And then every time you will get the environmental lapse rate. So this phenomena is called as the ambient lapse rate, yeah, environmental lapse rate. So it is the measure of the atmosphere stability actually, how the stability is that atmosphere. So we can generally denote as dt by dz here. This is the lapse rate, environmental lapse rate. Two types of lapse rates are there. Number one is the adiabatic lapse rate, and number second is, and adiabatic lapse rate are having a two types again: dry adiabatic lapse rate and wet adiabatic lapse rate. Okay, so number first is the adiabatic lapse rate, and there are the two types again: dry adiabatic lapse rate. I will be calling as DALR, and this is wet adiabatic lapse rate, WALR. Okay. So any warm air parcel, if it is rises into the atmosphere for every 1 kilometer rise, changes of the temperature is minus 9.8 degrees Celsius. So dt by dz you can get it minus 9.18. This is a change of temperature delta divided by 1 kilometer. So you will be getting a minus 9.8. And you can write it minus 1 degree Celsius divided by 100 meter. So ALR is always constant. Yeah, adiabatic lapse rate will remain always constant. So there's an adiabatic law for gases that I will talk later. Okay, it does not change from time to time and place to place. Cooling and heating process of air pockets. Uh, I will explain this mechanism. This is a natural process actually, how the cooling of waves, cooling of air will be taking place, and how it will be heating of, like how the heat exchange and because the conduction and convection process will be taking place for the air, wind, the hot air as well as the cool air, right? So there are the various air pockets. So in the air, it is said that in the air, the cooling and heating process will be assumed. We are assuming like it's a adiabatic process, and the PVQ over gamma is equal to, say, this is thermodynamics that I will discuss later. Okay. So as the air parcel moves up, its temperature decreases as its heat energy is expended due to the increase in the volume of the air. This is the common phenomena. So you see there, this is the height on the y-axis and temperature on x-axis, and this is the environmental lapse rate. Darker one is the environmental lapse rate, and this dotted one is the adiabatic lapse rate. So adiabatic is the ideal conditions, but we assume that the whole atmosphere, the lapse rate will be considered as adiabatic only. Okay. So everywhere you can put a slope and then x-axis and y-axis, you can get the ratio, right? So suppose here you can put a slope and then you can get a environmental lapse rate. This is a common phenomena. So if the air pocket air parcel moves up with the temperatures, its temperature start decreasing, and it's like releasing the heat energy, and heat energy will be used for the cooling air. There's a cool air and warm air, so heat energy will be supplied from the hot air to the cool air, from the higher temperature to lower temperature. So there's a convection process will be taking place. Yeah. So what is happening here in the whole process and mechanism, in the stratosphere mechanism, once this air pocket moves up, the temperature goes down and heat energy is expended due to increase in the volume of the air. The dry air expanding and cooling adiabatically cools at a 9.8 degrees Celsius temperature per kilometer. Suppose in this example they have taken it, an example they have taken in that example. So it is called as a dry adiabatic lapse rate. And saturation, a saturated wet air, this rate is calculated to be a 6 degrees Celsius per kilometer. And this is known as the wet adiabatic lapse rate. So these are two adiabatic rates here, dry adiabatic lapse rate as well as the wet adiabatic lapse rate. So actual adiabatic lapse rates neither dry nor wet. So in between it will be. So consider a rising parcel of air. As the parcel rises, it will adiabatically expand and cool. Adiabatic is a process where the parcel temperature changes due to an expansion or compression process. No heat is added or taken away from the parcel. Okay, so that is the constant rate. Adiabatic lapse rate is the constant rate. There is no heat exchange taking place, no addition, no taken away, and the partial temperature changes due to then expansion and compression. So simultaneously expansion will be happening. On the other side, compression will be happening. So there is no, so it will be balance reaction actually. Stability of the environment is determined, as I told you, depend on the adiabatic lapse rate and environmental lapse rate. Depend upon the relative position of two lines. These are the two lines: ELR, environmental lapse rate, and this is the adiabatic lapse rate with respect to height and temperature. So with these both lines will keep changing. Based on this, stability will measure. So I will be talking about the stability part. There are one by one I will come. There's this atmospheric stability. Atmospheric stability determines whether or not air will rise and cause storms, sink and cause clear skies, or essentially do nothing. Stability is dependent upon the dry and saturated adiabatic lapse rate and the environmental lapse rate. So whether you are going to determine what will be the condition into the atmosphere, whether atmosphere is stable, whether atmosphere is suitable for the pollution dispersion or not, more dispersion will be happening, more dilution will be happening, means there is the more chances, then quickly the pollutant will disperse easily, the sky will be clear. Okay, if there is a dispersion slow, if there is less dilution, means the more time will take to or take away the pollutant. So it is very important to understand the stability, and it depends on weather condition, temperature, as I told, wind speeds, pressure, everything above that. So this is the stability of the environment. This is the height, and these are the various graphs: height versus temperature. This is the environmental lapse rate. This is the adiabatic lapse rate, and this is the isothermal condition. So both are keeping away. This is a stable condition right now. What environment? This is the dry adiabatic lapse, and this is the wet adiabatic lapse rate. Yeah. So these three lines will decide the stability criteria. This is the stable condition, and this is the unstable condition where the environmental lapse rate is far away from the adiabatic lapse rate, and this one is down. Okay, I'll be talking later about all this. I will come back for this graph again. So what is the basic concept here? When the temperature of the air parcel is greater than the temperature of the surrounding environment, then it will rise, and when the temperature of air parcel is less than the surrounding the environment, then it will sink. There's a two conditions: sink and float. So both conditions will depend on the temperature. Okay, if the temperature of the air parcel is greater than the temperature of the surrounding, then it will rise, and when the temperature of the air parcel is less than the surrounding, then it will sink. So environmental lapse rate, there are the three conditions. We will be talking here about the three conditions. Uh, these three conditions we'll be talking here: a stable, unstable, neutral conditions. Okay. So one condition, there's the first condition, the environmental lapse rate, which is less than the dry adiabatic lapse rate. So some of the terms are new for you, I think. So don't get scared here. So you have to understand the environment. If you have studied as elective your air pollution control, then you can easily getting my point. If you have not taken elective, then it will be a new thing for you. So there's the environmental lapse rate, which is less than the dry adiabatic lapse rate. This is one condition. Here ELR is less than the dry adiabatic condition. What is going to happen in this? A rising air parcel becomes cooler and more denser than its surrounding and tends to fall back to its original position. Such an atmospheric condition is called as such an atmospheric condition is called as stable, and the lapse rate is said to be a subadiabatic. So in the environment, if the ELR is less than dry adiabatic lapse rate, then subadiabatic conditions will be taking place. Number second is the under stable conditions. This is very little vertical mixing, and pollutants can only disperse very slowly. As a result, their levels can build up very rapidly in the environment. Third one is the instability condition. Uh, yeah, unstable condition. Just a minute, 1 meter. So here we were talking about the environmental stability rate, okay, and there are the conditions for it. Altitude with respect to temperature. This condition is called a stable condition where ELR rate will be less than to what we called as ELR rate. And the unstable condition, highly unstable condition is when the ELR rate is greater than to the ALR rate, adiabatic lapse rate. So this is unstable condition. And there is one condition where ELR rate is equal to ELR rate, which will be called as here, which will be the neutral condition. So stability and instability of the environment will be decided based on these rate only. So first condition we will be talking here. It generally occurs at 4 p.m. to 7 p.m. in this timing, and it's a highly unstable condition. What will happen in this case? The partial of air will continue to accelerate in the direction of displacement. Dispersion will be rapid due to the marked vertical mixing of air. Rising partial of warmer, lighter air will continue to lift up, whereas a partial of heavier, cooler air will continue to come down. Good for the pollutant dispersion. This condition is good for the pollution dispersion. The ESR prevailing ESR is known as the super adiabatic lapse rate. Sometimes we call it as a super adiabatic lapse rate. Okay, and this condition is good for the environment. It's an unstable condition because a highly unstable environment will be good for the pollution dispersion. This is the simple concept for it. So the environment is highly unstable when it will be when the ESR is greater than ALR. In that condition, it is good for the pollution dispersion and easily the sky will be clear from the pollution. The second is when the ESR is less than ALR, it will be occurring in the morning hours 8 a.m. to 11 a.m. Stable environment it is, as I told you. In this condition, the prevailing ESR is called as a subadiabatic lapse rate, bad condition for the pollutant dispersion in the morning. So generally in the winter season, right, the fog and all that. I will talk later about the fog, how the inversion will be taking place and all that. Okay, so this is the bad condition for the pollution dispersion. Third one is the ELR. This is called as negative lapse rate, occurs at midnight, generally in midnight. So this is the negative lapse rate. Temperature increases with the altitude. Then dt by dz is known as an inversion. So dt by dz will be equal to positive, and then it will be the negative lapse rate, which is called as an inversion. Now, during inversion atmosphere, it is said to be highly stable atmosphere, and it is worst for the pollution dilution as well as dispersion. Smoke won't rise above 5 meters, above 50 meters in that condition. So inversion is the highly, we can say, stable environment, which is very harmful for the nature because pollution will not happen. Pollution will not disperse. Dilution as well as dispersion will not happen. Okay, in this case, I'll be talking later about the inversion in detail. These are the ideal conditions. Fourth one is the ideal condition where the ESR equal to ALR. Both lines coincide each other, and this is the neutral environment. This is neutral environment. So you see there, this is the temperature as well as this is the altitude, and this is the super adiabatic, which is far dotted is the adiabatic, and inversion from all three conditions. And this is the for now I'm coming for these. Yeah, you see here adiabatic lapse rate, ESR, and this is the ideal conditions. So all three types of conversions are happening here. So this is a stable, unstable, and this is conditionally unstable. And we can say the neutral. Dotted dry adiabatic, most adiabatic, ESR as well as the adiabatic lapse rates. So if this heading means ELR is equal to ALR, then the neutral environment conditions will be there. So this one we have taken as LR, this one we have taken as the ALR. Okay. And this is the dry adiabatic line. So I'm just coming for the graph. Here also we have temperature versus altitude. This is dry adiabatic lapse rate and all that, how the temperature inversion will be happening, right? Super adiabatic lapse rate. Yeah. So there is a gases law that we have to understand for the dispersion and dilution techniques before studying the dispersion and dilution. I will be taking a 2 minutes for it for explaining. explaining these gases law, then I will be coming for the main topic that we want to discuss today. So this is a hydrostatic equilibrium. dV by dz is equal to minus rho into z. Perfect gas law you have studied in thermodynamics part. U is equal to n into R into T. Ru is the universal gas constant in Newton to meter per mole into Kelvin. In your 11th, 12th also you have studied this, and in your engineering, first year engineering also you have studied these things, right? Gas laws. So generally, then physics also they keep talking about it. 8.314 T is the absolute temperature of gases in Kelvin. You just refer this PPT. I'm not going for the details. Only main point I'm covering from the gate point of view. And temperature will be plus 273. You have to take 273.16. You have to add in the standard degree Celsius temperature. N will be the number of moles of gases. V is the volume and humidity of the gases. And number of moles of gases is equal to mass of gas m per molecular mass of the gases. So small m divided by capital M. Small m divided by capital M. So generally small m will be the V into rho, and you can write it in that final form, and number of moles of gases will be you are getting in small m by capital M. So it will be V into rho divided by m naught, mass density and all that. Okay, these are the three laws that we speak that we talk in the gaseous forms. One is the Boyle's law, Charles law, and Avogadro laws. And then Boyle's law says that the all laws are talking in terms of volume, in terms of pressure. Okay, so the Boyle's law always says about the pressure and volume, and then Charles law says volume versus temperature, and Avogadro's law says volume versus the number of moles. So relations is important. So RU by M naught is the gas constant denoted by R finally. This Ru, whatever we have taken Ru here, this Ru, if we divide it by m naught, this is molecular weight of the substance, will give the complete R. This is the universal gas constant. For the dry air, the value will be 287 joule per kg into Kelvin. For the water vapor, Rw will be 462 joule per kg into Kelvin. So dP by rho, this is the standard equations. If you go for the PV is equal to RT, that equation, if you use it, if you put all the constant, then you will be getting this form. This is called as the hydrostatic equation. Dp by P is equal to minus G by RT into dz. So we can consider the adiabatic atmosphere. So as I told you earlier also, we always consider the adiabatic atmosphere conditions. So adiabatic Lapse rate, we will take it. So through the thermodynamic law of adiabatic expansion, will be coming here. So this is the general calculation. PV is equal to RT, and then derivative with respect to dV and volume, right? That will be the pressure. P into dV plus V into dP is equal to V into R into dt. If you go for it, further solve it. This is the specific heat at constant pressure and specific heat at constant volume, Cv by Cv. So Cv plus R divided by Cv. These are the normal we can say the derivations that you have multiple times done it, and then you know the standard values from gases laws. So if I'm talking about the adiabatic conditions, so there's the adiabatic condition, the law will be different. PV to the power gamma is equal to constant generally for the adiabatic conditions. So gamma is the gaseous constant, and then if you talk about the conditions, T into V to the power gamma is equal to constant. If you talk about the potential, will be like. There's a three relations, 1, 2, 3, as well as this one is also important, and that one also, this one is also important while you're talking about the gas law. So these are the questions to be made. So you can just solve it. So they have this gamma is the equation. Yeah, so it got disconnected. Yeah. So here, yeah. So these equations you can do it. I have already circulated I think notes for this. You just try to solve the questions and go for the series also GATE series. We have hardly 1 month for GATE exams now. But basic theory part and basic equations derivations I have explained everything, and standard equations that is used. We just go through these numericals and then try to solve it. So once you go through these slides and air pollution slides completely, you will be getting enough confidence for attempting the questions. Okay, related to gases. Okay, so this is the formula for D minus G into Mg by Cp, and then you conversion you can do it. Joule is 1 joule is equal to 1 Newton into meter, which will be if you want to convert into kgs, then kg into meter per second square into meter. Then conversion you can do it, and finally you will get as minus 9.8 degrees Celsius per kilometer. Now, you're talking about the negative lapse rate. Yeah, inversion, that is very important. So, there's the fourth type, as I told you. Okay. The another thing is Dale TSR. Sometimes there is a two temperature given in the question. The temperature for TS and TA will be given. So higher minus lower, if you can do it, you will get the temperature for the ESR, yeah, ELR, environmental lapse rate. So will be equal to the ratio you can calculate. So there's a altitude versus temperature graph. Through this, you can get this. Okay. So the very basic equations you can solve. So inversion, what is inversion? When the temperature of environment increases with altitude, then the lapse rate becomes inverted or the negative from its normal states. Inversion, it's a state in which the warmer air lies over the colder air below, and higher stable environment, highly stable environment, and it is very bad for the pollutant dispersion. There are the two types of inversions. Number one is the radiation inversion. Number second is subsidence inversion. There's the two type mainly. So first, we'll talk about the radiation inversion. This phenomena occurring from the unequal cooling rates for the Earth and the air above the Earth. When the Earth cools rapidly, the more quickly than the air above it, then naturally the temperature in the environment will be less at the Earth and will increase above it. It can extend few meters into the friction layer, break up easily when the ray of morning sunlight comes. Okay, so this phenomena is having a certain temperature ranges, and generally on the surface temperature rises, and it's this phenomena occurs early in the morning. This radiation inversion occurs in the morning, and morning it can easily break this layer. So yeah. Such inversions help in the formation of fog when the air is wet, simultaneously catches gases and particulate matters as it stops their upward lifting, therefore creating a concentration of pollutant in our closed environment, more common in the winter. Longer nights, because of the longer nights that happen in the winter. In the valley areas also, this practice is very common. Radiation inversion is very common. In valley areas, what will happen? Also have such inversion frequently because of the absence of horizontal movement of air due to surrounding high ground. Okay, so that is the techniques. Then this is the process inversion, and then second is the subsidence inversion. It happens at a high altitude, high pressure system, sinking or subsidizing motion of air in a high pressure area surrounded by the low pressure area. There's an anticyclone. The air circulates around the stationary high pressure, descends gently at 100 meter per day and 1000 meter per day. As the air sinks, it is compressed and get heated to form a warm dense layer over the cooled air below. So there's a cooled air and the warm air, and then because of the wind speed, because of the temperature and pressure profile is different for the particular area, and these thing conditions will occur. Okay, so generally anticyclone conditions will occur when the such inversions politics will cause the concentration of pollutant to increase. If the height of the inversion is less than 200 meter or so, the extreme pollution will occur. more dangerous. Both inversions may also occur simultaneously sometimes. Known as double inversion or first step of inversion will be complete. Inversion will be taking place together simultaneously. Then this condition is called as double inversion. All conditions are adverse for the environment. It is not good for the pollution. Pollution we want the quickly the pollution and particulate matter dust and all the pollutants should disperse so sky should be clear. Now, second is the impact of wind on dispersion pollutants. This environmental let's see it in everything we have studied. Second impact we have for the direction wind speed play a very important role in that. There is a windrose diagram. By going for this analysis for the windrose diagram, through this the meteorological department will calculate the weather and this wind speeds and all that, right? For the atmosphere as well as the pollutant dispersion, right? How the pollution, suppose the particular pollutant is released from the particular industry. So I'll be talking about the various types of plume function. Okay. Generally, the air winds, horizontal movement, a transport of the pollutant in atmosphere depend on the winds. If there is no wind, then pollutant will not disperse. So it helps in dispersing the pollutant as per this wind. And wind in atmosphere represent unstable conditions. No wind conditions give quiet and calm environment, which is stable environment, which is very harmful for the atmosphere for pollutant dispersal. Um, Wind at a place is measured by anemometer. There's a device called a anemometer which will measure the wind speed. There's a wind vane also, wind direction, on which direction wind is going. That also through the wind vane you can measure it. And there's a wind speed at any high altitude can be measured by the 1 by 7th law. There is a 1 by 7th law in wind speed measurement, which is will be equal to V by V naught is equal to Z by Z naught to the power 1 by 7. So this law is called as 1 by 7th law. So sometimes they ask in GATE questions. Suppose we have given a 2, 3 questions here. So this is the 1 by 7th law for measuring the wind speed with respect to altitude. So suppose an anemometer installed at a height of 3 meter recorded a wind speed of 2 meter per second. What is the wind speed at a height of 300 meter above the ground? So just use this equation and get that. So V by 2 velocities are given, divided by height, altitude is given 300 divided by 3 to the power 1 by 7. You will be getting roughly 3.86 meter per second. V you are getting it. So recorded at a 3 meter height, recorded wind speed is there. What will be the recorded wind speed at a 300 meter height? So that you have to use this relation and you will get the height at anywhere along with this altitude. So this is the wind speed we have taken on x-axis and height we have taken on y-axis. So this is the graph you are going to plot it, right? So this is the 1 by 7th power law through this blue lines where we have shown it 1 by 7th power law. Anywhere you can get it. The wind speed you can measure it by using this equation. Now we'll be coming for the windrose diagram, which is very important. This is the windrose diagram. Wind speeds, generally the forecasting, weather forecasting, and these meteorological department used to go for it. Okay, the wind direction, speeds, and everything will be noted down through this windrose diagram. So wind data at a place is represented by using the windrose diagram. Windrose diagram is a tool which sharply displays wind speed and wind direction at a particular location over a period of time. Meteorologists use windrose diagram to summarize the distribution of wind speed and direction over a defined observation period. The diagram normally comprises of 8, 16 or 32 radiating spokes, which represents wind directions in terms of cardinal wind directions like north, east, west, when we were studying, we used to create a scale and yeah. So lastly, windrows diagram. So to extend the wind speed and wind duration, either we can run here for longer, right? So this windrows diagram helps in this. The length of each spoke or segment are related to the frequency that the wind blows from a particular direction for each particular spoke or segment. Each concentric circle represents a different frequency, starting from zero at the center to the increasing frequency at the outer circle. There's a mechanism, there's a systematic procedure for drawing this diagram, these windrows diagram. So windrows typically uses 16 cardinal directions such as north, north-northeast, northeast, etc. Like the 16 combinations. Although they may be subdivided into as many 32 directions, in terms of angle measurement in degrees, north correspond to 0 by 30, 360 degree, east to 90 degree, south to 180 degree, and west to 270 degree. So we have to, based on this, there is a scale and then you have to plot it. In GATE exam, they will not ask for plotting and sketching this and all that thing, but the simple concept they will be asking. So this is a windrows diagram they have given. Percentage is given in spokes. If 4%, 8%, 12%, 16%, 20%, right? So typical wind diagram. Uses of windrows are very like in right now it's very effective. Sailors use windrows Is it audible now? Can you hear me? Pavitra, can you hear me? Is it audible?
Yes, sir.
Now can you hear me?
Okay.
Okay. So this is a windrows diagram we are talking. So sailors are using this, architects also use it. Those information inside stadiums. Even the aircraft engines also, commercial aircraft and all that, where the pilots are using the information, the wind speeds and wind directions and all that, with respect to time and very altitude. So that information. So wind power forms, windmills do extensive use windrows diagrams and studies primarily for their wind turbines. Also used for siting of industries in order to minimize the impact of your hydroelectricity. I'll talking about the plumes. These plumes are very important. Plumes is nothing but these from the stake of the chimney. This pollution is dispersing, right? So they are these smoke is making its own path, right? this path is called as the plume formation. So in what direction, which plume path will be good for the collision dispersion? So suppose here see that there's a plume which is going in this direction. Some this plume is going on the upward direction, right? Some of the plume is directly coming towards the downward direction. So it depends what type of seed that smoke is forming while it is dispersing, while it is releasing from the stake or chimney. That is very important while you are going to understand the dispersion of the pollutant to the air. That is very important. That is called as plume behavior. So there are 6 8 types for it. So studying one by one plume behavior. One is the looping plume. This is the looping plume. It will make a loop once it is released. This from the stake of the chimney. Once the smoke is released, pollutant is released, it will make a plume, looping plume. The high degree of convective turbulence, super adiabatic lapse rate, strong instabilities, associated with clear daytime conditions, accompanied with a stronger solar heating and soft light winds, high probability of high concentration at ground level close to stake. So high probability of high concentration at ground level close to stake occurs in unstable atmospheric conditions. This is called as looping wave. And that you have to relate with the adiabatic lapse rate as well as the ELR rate for the stable and stable in neutral as well as the inverse conditions are there. So loops behavior and looping plume behavior will be close to the unstable conditions that told about. ELR is greater than ESR, ELR. So you see we have compared both the things here. Uh, this is your ELR, environmental lapse rate. This is your adiabatic lapse rate. Both are far. This condition was here the ELR is greater than your ADR. This is the ELR. ELR is the adiabatic lapse rate. ELR is the environmental lapse rate. So ELR is greater than this. So this is the unstable conditions. The behavior will be like this, and this is the plume formation. It's a highly unstable condition. Second is the conning fluids. This is the con. The con say once the pollutant is dispersed, is released from the stake of the chimney, it will go in a plume behavior, a conning behavior. It will form a conic sections, right? Conic shape. This is the condition. This is a stable condition in small scale turbulence associated with overcast moderate to strong winds. Roughly 10-degree con will be formed. Pollutant travel fairly long distances before reaching ground level in significant amount of it occurs in a neutral atmosphere conditions. So this is the conning condition which occurs in the neutral conditions means ESR is equal to ALR. Both will be equal. They coincident. Right? So 10 degree of con will be there. This the condition will be highly stable. You see here this is the conic conditions. We have the adiabatic lapse rate and environmental lapse rate, dry adiabatic lapse. Both the two things are coinciding here, ELR as well. So this is the conic. The neutral condition. What was the condition that we have taken for the environment? Neutral conditions. Versus 2. Now it is fine. Now it is clear. Please respond. We will wind up the session. So here we have gone through this behavior, explaining about yeah, yes, sir. The stable conditions, neutral condition, is stable condition. This is the conning condition. And the third one is the fanning fluid. This is the fanning plume. It will be in a fanning shape. So it will go like this, and then the equal volume, same height. It will go for the certain height first, and after that it will disperse in a straight horizontally. So then after passing through the certain distance, it will go down on the surface, on the ground. So occurs under the large negative left state conditions, strong inversion at a considerable distance above the state, burst condition for the atmosphere. So fanning plane is the burst condition, considerable distance above the state in extremely stable atmosphere. Extremely stable atmosphere, as I told you, the pollution, the stable atmosphere is not good for the environment. The voice is audible now clearly. Jasurya, is it clear my voice? This is a 10-minute session only with wind ups. Can you hear me? Is it audible? Please respond someone. Jasurya,
Sir, it is still low. Your voice is still low, sir.
still also okay. Just give me a minute.
Yeah. So this is the fanning plume condition where, as I told you about the fanning condition, this is the very stable atmosphere. So a very stable, extremely stable atmosphere is not good for the pollution dispersion. This is a bad condition for the atmosphere. And a little turbulence. If plume density is similar to the air, travel downwards at approximately same elevation. So it will pass. It will go through the particular elevation. It will go, and it will travel some distance. After that, it will disperse into the on the ground. So this is the condition for this fanning condition. Adiabatic lapse rate and environmental lapse rate both are crossing, and it will go like this. This is a bad condition for it. Now this is the lofting plume. This is the fourth condition, lofting plume. Lofting plume will be like this. If you put a straight line over there, it will not go down. It will not go down below this level. It will be straight. It will increase the height of plume above this line, not the down of this line. So this is a lofting plume. So lofting plume favorable in the sense that fewer impacts at the ground level, pollutant go up into the environment. They are created when the atmospheric conditions are unstable above the plume and stable below. So this is the condition the, uh, for the lofting condition. So here the adiabatic lapse rate and environmental lapse rate will go like this, and then finally it will become a approximate parallel to the adiabatic lapse rate. So it will be like this. From that part, this height, you escape it and you make a straight line over there. It will be a straight completely. So this is unstable condition. Unstable conditions are good for the pollution dispersal. So this is good. There's generally the comparison. Anything they can ask in the GATE exam about the all concept, any concept they ask. So which that you have to say 7, 8 types are there that you have to understand which one is good, which one is stable. So they can ask the multiple select questions like highly unstable, fumigation highly unstable, good for the atmosphere, good for the environment. Yeah, ESR questions also they ask. They can ask the combination of your the plume behavior as well as plume behavior with respect to ESR, ELR as well as the ALR. That you have to compare. I have a, one slide where I have accumulated everything that is good for you. That I will come later. I will go later once you understand everything. Fumigation is most dangerous plume. Contaminants are all coming down to the towards the ground. See there, they are created when atmospheric conditions are stable above the plume and unstable below. This will happen most often after the daylight sun. जय सर आप मैं आता हूँ सर कुछ देर में आता हूँ सर थैंक्स they are created when the atmospheric conditions are stable above the plume and unstable below. Above there is a stable condition, below there is an unstable condition. This happens most often after the daylight sun has warmed the atmosphere, which turns a nighttime a fanning plume into the fumigation for about half an hour. So this is the condition for this is the condition for this pollution dispersal. So the surrounding area, the whole area, the pollution will be traveling towards the ground, no? So it is not dispersing into the atmosphere. It is not going towards the stratosphere. It is going towards the ground only, and it is not traveling a too much of distance also. So the surrounding area, surrounding whatever the area is there, the whole kind of pollution will be dispersed into the atmosphere, into the or maybe on the ground only. This is the condition here. Here, adiabatic lapse rate and environmental lapse rate. So dotted we have considered as the adiabatic lapse rate, and this is the ESR. So this will be the relation for it. And this graph will be don't get confused here. Like this. The comparison sometimes. Trapping plumes when inversion both below and above stake height. Trapping results. The diffusion of pollutant is severely restricted to the layer between the two stable regions as shown in the figure. See here. This is the one dotted line on the above of the pollutant. Below of the pollutant, this is the chimney from the air effluent is discharged. So pollution is dispersed and it creates an inversion condition in where it's kind of block here. It's kind of anticyclone inside. So it is very dangerous, and the behavior of ESR and ALR will be like this. Like this. Environmental lapse rate with respect to time distance. So this is the sixth condition for this. Then seventh is the neutral plumes. It tends to rise vertically until it reaches the air density similar to that of the plume itself. It is often converted to conning if wind velocity is greater than 10 meter per second and when cloud overblocks solar radiation. This is the condition for neutral plume. So altitude with respect to temperature. This is neutral atmosphere. So environmental lapse rate and dry adiabatic lapse rate and adiabatic lapse rate. And plume will be going towards the smoke will be going on the top of the top there only. Light winds, wind speed is low here. Clear skies in neutral atmosphere. Okay. So the finally it will travel for the certain height and it will disperse into the atmosphere. It is stable condition, neutral condition. You see here captured near this is from the chimney. It is going up only. This is the maximum mixing depth and we don't have a time for this. Okay, you just I will just send you this PPT. You just go through that. You will get an idea about it. Okay. So plume behavior I have explained here also. Various plumes, loopings, and all that. There. You see here, there's the comparison we have in the one slide. We have explained here everything. This is the elevation and temperature. This is the looping condition. This is the conning condition. This is the fanning condition. This is the lofting condition, and this is the fumigation condition. This is the trapping condition. These conditions should be in your tips only. Stake height and dispersion. So that is the highly technical. You have to go for the various derivations and numericals. You have to do it. The plume concentration, plume center lines, and all that. Okay. Yeah, so that's all for today. Wind up the session. Okay. Control and measurement part, I will take another 5 minutes. That is also important. Control and measurement of pollution. We've studied everything. That is also important. So control and measurement part, there is a hierarchy for the environmental pollution control. Environmental pollution control. The like the pyramid, no best pyramid we have considered for the solid waste also. The same way we will be having a pyramid diagrams. This is like this. Yep. So this is the environmental pollution management hierarchy: prevention, minimization, treatment, disposal, and abatement. We have always prepared. So first of all, that you have to reduce the pollution at the source itself. You have to prevent the pollution at the source itself. Suppose some kind of pollution is releasing from the thermal power plant, then you have to stop the pollution there itself by using the partially or fully. You are if you use the more sustainable and biodegradable fuel rather than using a coal. So if you replace coal, or you just stop that coal plant and you go for the renewable energy sources like solar, wind power plant, hydropower plant, right? And you can go for the geothermal power plants, right? These are the more sustainable way of energy generation rather than being dependent on thermal power plant and conventional sources of energy. You have to shift it into the renewable energy sources, so that we have prevented the pollution itself, because there is no coal burning means pollution will not be there. For the emissions, automobile vehicles, what you will do, rather than being dependent completely on the automobile vehicle, the fossil fuel based emissions, we replace the fossil fuel by using electric cars, by using biofuels, by using biodiesels, by using bio CNG cars, right? So if you replace the fuel itself, so combustion will be not happening in the internal combustion engine. Of course, the release of carbon monoxide, SO2, NO will not be there, and there will be the reliable material like the as I told you, the biofuels, biofuels, biogas, then the pollution will not come out from at all from the source itself. So these are the prevention is a very effective technique. It's highly prepared, most prepared. And then if the particular industry is releasing a pollutant like the various automobile industries, manufacturing production sectors, steel manufacturing industries, you have to partially or at least 50% you have to replace by the SDF and RDF fuel. So SDF and RDF fuel are more renewable, more sustainable. Then we can prevent the pollution. And construction also, in building, in urbanization and building and transport, whatever the things you are doing it. And construction things also you can use a more sustainable material. So more sustainable material, if you are using it, then it is good for the environment. And the third thing is reusable, no, not reusable, the transport, like road transport, rail transport, and air transport, everywhere you are using fossil fuel, no, that you have to stop it, and that you have to use a more renewable energy source. Yeah, fossil fuel should not use that. So another thing, prevention. After that, minimization. If you can't prevent completely, then you have to minimize it. Minimize it means partial replacement of the fuel by using more sustainable fuel and all that, right? Biofuel, biodiesels. Other thing, using the public transport rather than using the private transport always, right? Personal vehicles should not use that much, and then public transport we have to use it, right? And 5 minutes. Okay, okay, okay. So minimization is a very good effective technique. If you minimize the air pollution by doing various preventions, and agriculture also using the pesticides and insecticides, if you use it less, then also environmental pollution can be reduced. Open burning should be stopped in open dumping side of municipal solid waste, as well as in the open burning should be stopped in the residue left in the agriculture farm. That also can stop the pollution at anyhow, right? So these are the various techniques that we can do it. Now, if you can't do anything, then is the treatment. That is the main effective technique. That is if pollution is coming, that you cannot stop it, then you have to treat that. For treatment part, you have to use various. There's, as I told you, there's indoor air pollution, outdoor air pollution. For controlling the indoor air pollution, you have to go for air purifiers and all that, right? For outdoor pollution, also nowadays you can put a big air purifier towers, so that way we can minimize the air pollution, right? Once you identify the air pollution is coming because of this only, then you can control it. And the treatment and abatement part, various engineering devices you can use it, right, for controlling the air pollution, like electrostatic precipitator, right? Electrostatic precipitator, wet scrubber, mechanical scrubber, right? These are the engineering devices that you can use it for controlling the pollution. Here it is. There is a cyclone air separator, cyclone air collector, wet scrubber, and the cyclone dust collector, right? Electrostatic precipitator. These are the air control pollution residue devices which has to be incorporated in the industries which are responsible for releasing the pollutants, right? So these are the pollution can be controlled from the industry part. Legislations, the rules and regulations should be very strict, and the government has to make the guidelines clearly. They should put the penalties. Pollution Control Board has to do the audit regular basis for the various industries while giving the environmental clearances. Public, the we can say the contribution is very important. So public has to be very aware about the pollution part, and they have to always protect our atmosphere. More plantation is required, right? Renewable energy sources uses, as I told you, right? These are the some things that we can do it for controlling the pollution. And before that, there's as I told you, the waste management hierarchy. That is prevention, minimization. This is always important. Regular maintenance of industrial setups and plants also can be done. Prevention of open burning of waste and e-transaction to minimize the refuse. Right. These are the various things that we can do for controlling the air pollution part. Okay. So these material I will circulate in your Google Classroom. You just download that and study quickly, and then write your exam. All the best for the GATE exam. So by this note, I will just bind up the session for today. Thanks for the CMRIT management as well as Panik Kumar sir, and those have given an opportunity to the classes, and we have to be very careful about the pollution part. We are here in the campus. So, okay, for this year it is fine. The next year will see for the next batch. Okay, we will bind up the session for today. Just I will take a screenshot for the attendance and then. Okay. Okay, then you can leave the class. Thank you so much for attending the classes. Any concern? Aishwarya, Chandana, Jasurya, Pavitra, Nati,
Sir,
Shweta. Any
sir,
question?
sir, can you send the PDF, sir?
हाँ हाँ मैं उसमें डालूंगा, राइट, गूगल क्लासरूम में आई विल upload the material in the library portal also. There is a separate folder, GATE classes karke, where all the recorded lecture I have uploaded already. This lecture also I will upload there only, and the PPT also, right? PPT and whatever the material is there I will upload. So just quickly revise the air pollution and control in part, and solid waste management also I have uploaded the material there. I will upload if remaining is there. So from my part side, environmental engineering is completed also. Okay. Okay then. See you.